listen please, when dealing with curves, we have indirectly or directly talked about this before. Let's even begin with quadratic, because the idea of curve exists from polynomial of 2 and above. If you have a polynomial of degree 1, that's just a straight line, so you don't talk about curve. So there's nothing like a turn somewhere. Stationary points are turning points, okay, where the curve changes direction, if we may put it that way. If you have a quadratic function, you know it's going to be in this form or this form, not both. A cubic function might look like this. It could also look like this. And some cubic function will just go this way and come down, depending on how it is defined. You will see a lot of them, but from my experience, I've seen cubic functions go like that, okay, where there is no turning point per se. Understand? So, what we want to do in this section is to be able to, without drawing the graphs, identify these points, label them, classify them, okay? And sometimes, some of this information might even help us to sketch what the curve will look like. I know we've done a lot of sketching graphs in functions, topic 2. Now we're having more information now to make us a better student when it comes to that section of math. So this is one of the usefulness of calculus. Now, in quadratic function, these 2 points, I will write this, so just listen. These 2 points are turning point or stationary point. Okay? Turning point or stationary point. This is called a maximum point, while this is called a minimum point. Understand? Because you know that this continues indefinitely. But whatever it is, no value of y on that curve can go beyond here. Understand? So the point, of course, is a 2 coordinates thing. A point consists of both x and y. So the value of b here is called the maximum value. Okay? But the point consists of both the x and y. Similarly, this is your minimum point of the curve. This point. Okay? Which means the y value here is the minimum value. And that is because every other value on the function, okay? So if a, for example, if b, if this is b and so on, this is a comma b, for example, it means for every x you take, f of x will be greater than or equal to b. Agree? To be greater than or equal to b. But when you have a cubic function, for example, you might be having both minimum and maximum, because there are 2 turning points. Okay? Here you have local maximum, here is local minimum. Now the word local and global, what does it mean? If you are sure, okay, let's see the difference here. In this curve, clearly, nothing goes beyond here. It's very restricted. So let's say this is a comma b, or that might be x1, y1, x2, y2, x3, y3, x4, y4. x5, y5, x6, y6. Here, you talk about local maximum and local minimum, because there is no ending. Something somewhere might be the maximum. We don't know. We don't care. Something somewhere might be the minimum. We don't know. We don't care. But within our neighborhood, this is our own champion. Understand? This is our own champion here. So we say local maximum, local minimum. Here, also local maximum, local minimum. But we can see that outside our neighborhood, somewhere far away, some guy was identified as a champion. Understand? So this would be the global minimum, and this would be the global maximum. Am I making sense? But if you have a curve like this, there is no global. The reason I didn't use those terms here is because it's a quadratic function. This is the only thing you can get. But if you use it also, I'll say local, whatever, fine. Are you getting my point? So at the turning point, you could see that the gradient is going to be 0 because it's parallel to the x-axis. Where there will be change in y, no, there will be no change in y, but there will be change in x. So at the turning point, the gradient is always equal to 0. We will get to that, some areas where we will use it. Now there are some other points that also could be encountered. The point here, we will see them later. They are called the points of inflection. They are points where the shape of the curve changes. So maybe I'll go to the shape of the curve next. The shape of a curve is used to determine, is it concave upward or concave downward? When we say concave upward, it means it's going up that way. When we say concave downward, it means it's going down this way. So a quadratic function, remember, this will be when your a is greater than 0, right? In my knowledge of quadratic. So a quadratic function with a greater than 0, you know what I mean by a greater than 0? Ax squared plus bx plus c. A quadratic function in this will always give you a concave upward shape. And this would be a concave downward shape. This is what I mean by the curvature of the curve. Yeah, just the curvature. So the shape of the curve is what we mean by curvature of the curve. We will also be able to use our derivative knowledge to identify, by looking at it, oh, this must be concave upward or concave downward shape. Now, for a cubic function, part of it we have concave downward, and part of it we have concave upward. Where that direction changes is your point of inflection. At the point of inflection also, your gradient is 0. We will see that very soon. In some cases, your gradient is 0. Look at this place is a point of inflection, and the gradient will always be 0. Okay, so we have some point of inflection with gradient 0, some non-gradient not 0. But there are two categories of your point of inflection. We can call some stationary point of inflection. Stationary point of inflection are the ones with gradient 0. From the idea of stationary points at gradient 0. But the ones like this are non-stationary points of inflection. Understand? So I'll take this one after the other. Let's start with the turning point. And I might be introducing more terminologies which I will explain. But I just wanted everybody to get a picture first. Does this make sense? All right, let's write some things down. Stationary points are also known as turning points. Some are maximum, local, global, some are minimum points, global, some are point of inflection. Consider following curves. the following curve. So let's start with quadratic one. Just got a new red marker. Someone taking it again? Okay, fine. Found it. So maybe we put some here. So I call this maybe figure 1. So I might use it in the curvature instead of drawing again. Or let's say figure A. I have to label that ABC. So maybe figure 1 would be better. Sorry. So this point A, this point B. More figure. Just a sketch, but the OCD mean will not let it go. Then I'll put a short note. In figure 1, A is minimum points. You can say local minimum. So I'll put the word local in bracket because we can say it without it. Yes, sir.
Can you move over to the right so I can take a picture of it? Thank you.
So 1 minute, I'll soon get out of your sight. In figure 2, point B is the local maximum point. Figure 3 C is global minimum. Okay. C is global minimum. F is global maximum. D is local maximum. Maybe I say 3 and 4 together. Figures 3 and 4. So D and H. D and H, just to reduce the writing. So D and H. Local maximum. achieve local minimum points. Does this make sense? Okay, let's take note of that. So for the curvature of point of the curve, okay, I might add 2 more points. Okay, maybe I just use this. Also, let's write curvature separately so you can. Of the curve and either the concave upward or concave down. The concave forward upward will mean figure 1, G. Figure 1, we have actually all boats. Yes, all the boats. In figure 1, we have concave upward ship. Figure 2, we have concave downward ship, while in figures 3 and 4 we have mixture of boats. So let's take note of that. Yes.
For point A and point B.
Speak louder, please.
For point A and point B, aren't they the global minimum and global maximum?
Oh yeah, we could say that. Usually we are silent with either global or local. You could say that because it's the maximum or it is the minimum. If it is quadratic, so yes, I agree with him. Maybe we could call that global minimum and global maximum because there is no other one elsewhere. So global will be the best term. I agree with you. Do you understand what he meant? So usually we are silent about it. So we can just call it minimum, or you can include the word global. Of course, only if it is quadratic. Okay? If it is quadratic, you know, this is the only shape you can get. There is no other way somewhere is going to change its course. Okay? So only if it is quadratic. Yes, you can just call it as global right away. Please take note. Thanks, sir, for that observation. All right. Let's see the usefulness of some of these things we've talked about. I'm a bit silent with the point on point of inflection for now, because I'm going to talk about that later, so I don't want to mix it too much. But we can actually discuss point of inflection immediately. Now, what happens to gradient at turning point? Because this is where we are going. So gradient at turning point. At any turning or stationary point, okay, the gradient is 0. And I think that is clear. At the turning point, your tangent will be horizontal. Is that not? And if the tangent is horizontal, gradient is automatically 0. So that's what we mean. So we're going to be using this to find out what is the value of x at a turning point and how that can be applied in different problems. You'll see a lot of economics problems, physics problems in the next few days. Okay? That is, if y equals f of x, then dy by dx, which is your f prime of x, will be equal to 0 at stationary point. The last thing I want to talk about is our sign diagram. Sign diagram of the first derivative. We'll still talk about the sign diagram of second derivative in discussing point of inflection. But for discussing the turning point, because if we know the sign diagram of the derivative, we know if this is a maximum or minimum. There's another way of getting it is finding the second derivative. We'll look at that. But we're going to see that for the first few problems we'll be solving, we'll rely mostly on our sign diagram. So maybe I put that here. This, I do not want anyone to sleep today, if you don't mind. We have so much to do. I mean, in terms of problem solving. Okay, let's look at it this way. Sign diagram of the first derivative. What does f prime of x represent?
The gradient of the tangent.
The gradient of the tangent to a curve, right? So if I have a curve like this, and the turning point is at point x1. This is x, f prime of x. Okay? This value represents x, this sign represents f prime of x. You will notice that there's a change in sign at x1, right? Before x1, what is the gradient?
Negative.
Negative. And after x1, what is the gradient?
Positive.
This is how you know the curvature. You could see clearly, oh, it was negative first, then, you understand that? So this is how we find the curvature sometimes. Understand? Again, if you have this case, where this is x2, I'm still on quadratic. So x2 is the turning point. What happens to the sign of that? Before, what do we have? And this? Oh, my bad. So clearly, oh, positive means it's going up, right? Negative means it's coming down. So this tells you the shape of the curve once you know the turning point. Understand? This is very useful, especially in curve sketching. The last but not the least that I want to mention, what if you have a cubic light function? Okay? Or which could also be the other way. So clearly there are two turning points. x3, x4, for example. And let's call this x5 and x6, for instance. Okay? What will the sign diagram look like? So there will be some x3 and there will be some x4. We are talking about the sign of the first derivative. Okay? Here, what is the sign? Again?
Negative.
Negative. And here,
Positive.
in between, it's positive. And here,
Negative.
I'm not saying this like positive. Like, look at it. It's coming down. Because we always look at it as x increases. So, just assume you're starting from this edge. As x increases, your gradient is negative. If you move forward, your gradient is positive. Again, negative. Can you see that? So finally here, we have x5 and x6. So the first will be
Positive.
positive, then negative, then kind of alternating, right? There are some exceptional cases where there will be no alternating. I think we saw something like that last time. When you have a square, something. Remember that? So let's take note. We will notice some things when we approach point of inflection. I don't want to put everything in one explanation. Does this make sense? Now let's solve a few problems to explain these things. I think number one in this exercise is not in your book. Okay, so maybe we do number one together. I'll project it now. We'll do that together. Let's look at the board. Look at this problem. I haven't mentioned point of inflection, but it's part of the question, so which is, you should understand. I will try to. The first question says the tangents at point A, O, and B are horizontal. Do you agree? Yes? So definitely the gradient is 0 at this point, right? So you can see clearly this is your, this the question. Classify point A, O, and B. Let's classify A and B. What is point A? How do you classify A?
Stationary.
Speak louder, please.
It's a stationary point.
Is the,
Stationary.
that's not classification, they are all stationary points.
Oh.
Local what?
Maximum.
Maximum, that's the classification. They are all stationary points. So when the question says classify the point, tell us what it is, not what they are. Alright? So A is a local maximum point because we don't know what happens, right? In fact, even if we know what happened, this is still our local maximum. Unless the curve ends here. If the curve ends here, then this will be the global maximum, this will be a local maximum. Understand? But the curve is going to extend indefinitely. What about B?
Local minimum.
B is a local minimum point. Here is neither maximum nor minimum, right? But it's also a turning point. We call this the point of inflection. That is what we are going into later. Understand? Now, the next question asks us to draw a sine diagram. So let's solve the question here. And I need everyone to be part of this, please. Let's try to solve the question. So A1. Let's see, sir.